This lecture will cover the first 3 weeks of development, and we will start with the fertilized egg. We're going to focus on the early development of the human embryo, looking at the first 3 weeks as the fertilized egg starts to move down the uterine tube to end up implanting into the uterus. During that time, we'll talk about the formation of the blastocyst, which forms during the first week of development. We'll then talk about the bilaminar disc, which forms during the second week. The bilaminar disc will turn into a trilaminar disc, undergoing the process we call gastrulation. This starts during the third week of development. The trilaminar disc then will undergo lateral body folding and head and tail folding, so that the vertebrate body plan is established by the end of the fourth week. If we look at this cartoon, we're going to make the point that fertilization occurs on day 1 of gestation, 14 days LMP, after the woman's last menstrual period began. The oocyte is fertilized by the sperm and then begins to travel down the uterine tube. The oocyte, the fertilized egg, is going to undergo cleavage, and that includes a reduction division where we now will end up at day 2 in a 2-cell stage. Both of these cells smaller than the original fertilized egg. The cells will continue to divide into the 4-cell stage at late day 2, and will continue to divide and as they do, they will form what is called a morula. And the morula exists at day 3, still located in the uterine tube. The morula is going to undergo changes where the outer cells are going to undergo compaction. That is to say, they will join one another via tight junctions and desmosomes, and separate then the outer layer from an inner mass of cells, which we're going to call the inner cell mass. So that by day 5 we have a blastocyst. The blastocyst consists of an inner cell mass surrounded by a trophoblast, and also within the trophoblast is a blastocyst cavity. It is this structure which will hatch from the zona pellucida, enter into the uterus, and if conditions are correct, will implant on about day 6 or 7 after fertilization. If we look at this image from the Pacific Fertility Center, we can follow embryonic development during this first week in these shots. First of all, in this upper image, we see an ovary. This ovary has been injected to supraovulate so that many follicles have developed, and here we're looking at each of the follicles. During in vitro fertilization, eggs that are ovulated are retrieved and fertilized in vitro. This next image shows a fertilized oocyte just after fertilization. You can see the 2 pronuclei. This next image shows the 4-cell embryo which we described, and below that an 8-cell embryo. This occurs at about the 3rd day of development. Here we can see a hatched embryo as it is about to make its way into the uterus. In this case, this will be injected into the mother's uterus, but in vivo, it is the hatched embryo that's going to reach the uterine cavity and then implant. So by the end of the first week, we have a blastocyst consisting of an inner cell mass, a blastocele or blastocyst cavity, and they're surrounded by a trophoblast. The trophoblast is going to give rise to the fetal components of the placenta. The inner cell mass is going to give rise to the embryo. In this image, we've simply taken the blastocyst and brought it close to the endometrial lining, the epithelium of the uterus, where if implantation is going to occur, it will occur in the uterine, along the uterine lining. We can also identify in the uterus uterine glands and uterine arteries that are found in the endometrium. Once implantation begins, the trophoblast cells are going to give rise to a second cell type. This is called the syncytial trophoblast cells. These cells will invade the endometrium, and the trophoblast cells will be renamed the cytotrophoblast. So the cytotrophoblast and the syncytial trophoblast are going to give rise to the fetal components of the placenta. We still have an inner cell mass, and we can still see the blastocyst cavity. During the second week, what will happen is another cavity will form. That cavity is going to be called the amniotic cavity. The amniotic cavity is lined by cells from the inner cell mass that we now call epiblast cells. The amniotic cavity is also going to be lined by amnioblasts. In addition to the inner cell mass giving rise to epiblast cells, they will also give rise to hypoblast cells. The hypoblast cells then will line what has now become the primary yolk sac. Prior to this, this was called the blastocyst cavity. So we changed the name to primary yolk sac once the amniotic cavity is seen. In addition to the hypoblast cells, cells of the exocelomic membrane line the primary yolk sac. All of these structures are surrounded by the cytotrophoblast. If we look at this website from the Human Developmental Anatomy Center of a 9-day embryo, what we can see is here the embryo that's implanted, and we can see the bilaminar disc with the hypoblast and the epiblast. We can see an amniotic cavity, and we can see a primary yolk sac. These cells are surrounded then by the developing placenta out here, where we'll see cytotrophoblasts and syncytial trophoblasts. So at day 10 of development now, the cytotrophoblast and syncytial trophoblasts have invaded the endometrium, and they've come into contact with the maternal blood vessels. The embryo itself is a bilaminar disc consisting of an epiblast and a hypoblast, and above the epiblast is the amniotic cavity. Below the hypoblast is the primary yolk sac. Surrounding the amnioblast and exocelomic membrane, that is surrounding the embryo, and between the embryo and the placenta, a layer of mesoderm will begin to form and is called extraembryonic mesoderm. The significance of the syncytial trophoblasts coming into contact with the maternal blood supply is that the syncytial trophoblasts can make human chorionic gonadotropin, HCG. The importance of HCG is it's going to feed back onto the corpus luteum of the ovary, which will continue production of progesterone. HCG is what is detected in the pregnancy kits that are bought today. And HCG can be detected in a pregnancy test by about day 14 of pregnancy, or at about 28 days after the beginning of the woman's last menstrual period. As soon as lacunae are formed and the blood supply then of the mother communicates with the placenta, then HCG can be detected. The next stage of development at week 2 is that spaces begin to develop within the extraembryonic mesoderm. You notice the extraembryonic mesoderm then surrounding the embryo with its epiblast and hypoblast, the amniotic cavity, and the primary yolk sac. If we look at this image from the Human Developmental Anatomy Center, we can see now this later stage of development. Here we have the embryo, there's the bilaminar disc, and now here we have that extraembryonic mesoderm, which is developing these spaces or lacunae within it. You can also notice the syncytial trophoblast coming into contact with these spaces in the endometrium, where we're going to have the maternal blood supply come in contact with the syncytial trophoblasts. A little bit later in development, what will happen is those lacunae will begin to coalesce and form a coelom called the extraembryonic coelom. So now what we will have is an embryo suspended by a connecting stalk, lying within this extraembryonic coelom. The extraembryonic coelom is going to become the chorionic cavity. There will be 2 layers of mesoderm that line the extraembryonic coelom, a somatopleure and a splanchnopluric mesoderm. In addition, we can see the amniotic cavity, primary yolk sac, the epiblast, and the hypoblast. Here you can see the connecting stalk connecting the embryo to the placenta. So by the beginning of the 3rd week, this is what the embryo looks like. A bilaminar disc in between an amniotic cavity and a primitive yolk sac sitting within an extraembryonic coelom. The next stage that's going to occur at the beginning of the 3rd week through the beginning of the 4th week is gastrulation. If we look back to this website one more time, we can see where at 15 to 17 days, this is what the embryo looks like. Now, the next stage of development during the 3rd week is going to be the bilaminar disc then turning into a trilaminar disc via the process called gastrulation. So if we look down on the epiblast, so we're looking from here, we're looking down on the epiblast, we removed the amniotic cavity and these cells surrounding it, what we would see is the following. We see the epiblast, here's the cut end of the amnion, and you can just see cut right here is the hypoblast underneath. The hypoblast is yellow, and then underneath that would be the yolk sac. Now, what's going to happen then during the third week is that we'll begin to get proliferation of cells located in this position, and these cells will continue proliferating in this direction. As you can see, here's the initial proliferation of cells, and a line of cells will continue to proliferate, moving in this particular direction. What this does is establishes a head region and a tail region, and the body axis is formed. So that by day 17 to 19 of gestation, if we go to the University of New South Wales and their embryology website, what we can see is the following. We can see the epiblast as we look down on it, and we can see these mitotic cells here forming what's called the primitive streak and the primitive node right at that position. Here we can see the primitive node and the primitive streak. Part of what is happening here is that for these cells to migrate, fibroblast growth factor 8 has to downregulate the E-cadherins. E-cadherins are important in binding epiblast cells together. So as they're downregulated, these cells that are proliferating can migrate down under the epiblast and migrate in further into the embryo. In addition, fibroblast growth factor 8 is going to upregulate this gene brachyury T. And this is a transcription factor which is important for forming mesodermal components. So for the formation of mesoderm and structures in the posterior body wall, we need this brachyury to form. If we look at the embryo then by taking a planar section through here and looking at it from the side, what we would see is the following. Here are the epiblast cells. The amniotic cavity would be up here. Primary yolk sac would be down here. These epiblast cells then are going to proliferate. They're going to lose their E-cadherins. They're going to move into this area, and the red ones, the red cells, are going to begin expressing the transcription factor brachyury and will become mesoderm cells. The yellow cells are going to become endoderm cells. So the cells of the primitive node and the primitive streak are going to migrate out, and they're going to become the mesoderm and the endoderm. Here we're showing the migration through the primitive streak of the mesoderm cells as they will migrate up deep to the epiblast cells and move in this caudal direction, that is towards the head. So the body axis is formed. One of the ways that this happens is that nodal is an important factor that initiates and maintains the primitive streak. In addition, bone morphogenetic protein and fibroblast growth factor also lead to the formation of mesoderm. Cordon, noggin, and follistatin are important in maintaining the cranial paraaxial mesoderm. In addition, things like HNF3 beta are also important for specifying that this is the head region. whereas brachyury, as we said, is important for mesoderm formation, in particular the paraaxial mesoderm in the region of the spinal cord and structures caudal to that. There is also left-right asymmetry which is going to form, and that's going to be regulated in part by things like fibroblast growth factor 8, nodal, lefty, and fibroblast growth factor is going to lead to the upregulation of nodal, which leads to the upregulation of lefty, which leads to PITX2 forming, and these are all factors that play a role in determining that this is the left side of the body, while snail is important for determining the right side of the body. So now we have a body axis formed, a head, a tail, a left, a right, dorsal, where the epiblast is, and ventral, where the endoderm is. If we look at this from the side, starting looking down in the epiblast again, where we can see the primitive streak and primitive node, what we want to point out is that in the midline, the development proceeds a little bit differently. So we're going to look from the side at the embryo cut in sort of this sagittal section. What we would see is the following. We would see this. So here's the embryo. Here we have what was the epiblast. We can now give it its proper name in the trilaminar embryo of endoderm. Here we can, ectoderm. Here we can see the endoderm, and in between we can see a group of cells which are going to migrate in around the primitive node. They're going to move in a cephalic direction towards the head. They'll fuse with the endoderm for a short period of time. When they do, a neuroenteric canal will form, and then they will round up again and form what is called the notochord. Again, cells migrate around the primitive node, form the notochordal process. If we look at this by taking a section through here and looking from behind, this is what we would see. We would see ectoderm, we'd see mesoderm, we'd see endoderm, that's the trilaminar embryo, and in the midline we'd see, at least initially, the notochordal process. The notochordal process will fuse with the endoderm to form a notochordal plate. When it does, a neuroenteric canal will connect for a short time the primary yolk sac of the amniotic cavity. That plate will then round up again and become the notochord, lying between the ectoderm and the endoderm, in between the mesoderm on both sides. This is a trilaminar embryo after gastrulation has occurred. So if we take a planar section through here, what we see now, to complete our story, is an amniotic cavity lined by amnioblasts in light blue, ectoderm in dark blue. We have mesoderm below it, paraaxial mesoderm, intermediate mesoderm, and lateral plate mesoderm. In the midline, we're going to have a notochord. And then deep to those structures will be the endoderm, which lines the yolk sac. So at the end of the 3rd week of gestation, this is what the embryo is going to look like. Again, this is from the University of New South Wales, and here you have your embryo. We're looking down at the epiblast now, and what we can see is some of the changes that we'll talk about soon in terms of the development of some of the ectodermal structures. But we're looking down on the ectoderm, and you can see this embryonic disc. You can also see the primitive streak still exists at this point. So we have the placenta, which is developing, a connecting stalk that connects it to the embryo. The embryo is surrounded by a yolk sac and an amniotic cavity, and the embryo consists of an ectoderm, a mesoderm, and an endoderm. I want to just make sure that we understand the timing of pregnancy. In terms of the embryology, we talk about gestational age starting with day 0. Day 0 is ovulation. The proliferative phase of the menstrual cycle is just ended. The ovarian follicle has ruptured. It's been ovulated. And this is day 14 of the menstrual cycle. Day 1, if fertilization occurs, day 1 of gestation occurs as the secretory phase of the menstrual cycle begins. This would be day 15. It would be the clinical age of the embryo. Clinically then, there is a 2-week difference between the gestational age and the clinical age. And the reason for this is clinically, the clinician will begin counting at the beginning of the last menstrual period as day 0. Implantation is going to occur day 6 or 7 of gestation, day 20 or 21 clinically. A bilaminar disc occurs at day 14 of gestation and day 28 clinically, and gastrulation is going to begin as the first menstrual period is missed. Gastrulation begins, that is about day 29 of an idealized menstrual cycle. I also want to point out that not all the fertilized eggs are carried successfully. In fact, only 30% are. So 70% of the fertilized eggs don't make it and are lost prior to implantation, or at least a third of them are lost prior to implantation, so that there's no hint of pregnancy. Of the other 40% of post-implantation pregnancies, all but about 10 to 15% abort spontaneously, and it's that 10 to 15% that are observed clinically. So roughly 25 to 30% of the spontaneous abortions occur so early they're not noticed either clinically. A lot of reasons for these spontaneous abortions, about 50 to 60% have chromosomal anomalies, though the very early losses is closer to 70%. In women as they age, there's a higher spontaneous loss, and there are other reasons for loss that are listed here. Many reasons why the pregnancy can be aborted early. A second point that we want to make, another point, is that as a woman ages, it's harder to get pregnant. Here we're looking at the chances of conception, that is in 1 month, in 6 months, in 1 year. And in the early 20s, a quarter of the couples will be pregnant in 1 month, and almost everyone within a year. By the time the woman reaches the late 30s, only 10% can get pregnant within the first month, and 65 to 70% is going to take longer than a year. So that the average time to conception increases as the woman gets older. And if you turn to this website, I'm not going to go over it now, but you can take a closer look at fertility over the years, where we consider some of the tremendous changes that have occurred that have altered fertility patterns in the United States.